Hello everyone, and welcome. Today, we're going to talk about Prism, a new system that tackles the massive cost of serving multiple large language models. We'll explore how Prism unleashes GPU sharing to make multi-LLM serving far more cost-efficient. This work comes from a collaboration across several institutions, and we're excited to share our findings with you. Let's dive into the problem we're addressing. The multi-LLM serving cost crisis is real, driven by massive GPU underutilization. Inference providers host thousands of LLMs, but dedicated GPU allocation leads to abysmal compute utilization, often as low as 1.3%. We need to reduce costs while still meeting strict latency requirements. So how do these unique workload patterns contribute to this crisis? These four key workload characteristics define the multi-LLM serving challenge. Model popularity follows a long-tail distribution, and models frequently experience long idle periods. Request rates also fluctuate rapidly. Finally, different models have diverse latency requirements. These characteristics demand a system that can adapt its sharing policies in real time. But how do current GPU sharing approaches fall short? Existing GPU sharing approaches simply can't adapt to these dynamic, multi-LLM workloads. Static partition methods, like MIG, waste capacity. Space sharing systems, like MuxServe, cannot dynamically adjust. Time-sharing systems, such as QLM, incur high latency overhead from constant model swapping. None of these offer the flexible, runtime adaptation needed. This is where Prism comes in, achieving superior SLO attainment compared to baselines. Prism's architecture is built on two core innovations. First, KV Cached provides on-demand memory allocation, decoupling virtual and physical GPU memory for dynamic redistribution. Second, a two-level demand-aware scheduling policy dynamically adjusts sharing strategies. A global scheduler places models across GPUs, and a local scheduler manages a shared request queue. Together, these components allow Prism to combine space and time sharing effectively. Let's dive deeper into KV Cached. KV Cached fundamentally changes how models share GPU memory. Traditional engines use static allocation, but KV Cached decouples virtual and physical memory using CUDA VMM APIs. This means physical memory is only allocated when needed, enabling flexible memory redistribution between co-located models. This crucial innovation for efficient GPU sharing only required about 20 lines of code change in SGLang. Fast model activation is vital for time sharing, as naive loading can exceed latency requirements. Prism uses reusable engine pools and parallel wait loading to slash activation times dramatically. This combined approach reduces activation for a large 70B model from over 7 seconds down to just 1.5 seconds. This 7x speedup is essential for meeting tight time to first token SLOs. Prism's two-level demand-aware scheduling intelligently manages resources. The global scheduler places models using a KV pressure ratio for balanced load and handles model eviction/reactivation. At the GPU level, a local scheduler uses priority-based admission control to manage requests, minimizing deadline misses. These two levels ensure both cost efficiency and high SLO attainment. Next, we'll look at how we tested Prism against existing solutions. We built Prism on SGLang and evaluated it on a cluster with 32 H100 GPUs, testing with 58 different LLMs using real production traces. We compared Prism against static partition, MuxServe++, and QLM. Our primary metric was SLO attainment for both time to first token and time per output token. Let's see the results of these end-to-end performance tests. Prism significantly outperformed the baselines, handling 2.3 to 3.5 times more requests while maintaining 99% SLO attainment. Baselines struggled due to their inability to dynamically adapt, leading to performance degradation or high swapping overhead. Prism's dynamic resource management is key, ensuring models receive necessary resources when demand surges. This flexible approach translates directly into better cost efficiency. Prism dramatically reduces the hardware needed to meet performance targets, achieving 99% SLO attainment with half the GPUs required by current baselines. For 58 LLMs, Prism needs only 16 GPUs for 99% TTFT attainment compared to 20 to 32 or more for other methods. This results in more than a 2x reduction in GPU infrastructure costs, a major advantage for large-scale LLM deployments. Prism's on-demand memory allocation, KV Cached, enables dynamic KV cache redistribution. When one model becomes idle, its memory is immediately freed and available to active models, contrasting sharply with static partitioning, where idle memory is wasted. This dynamic memory pooling allows for larger batch sizes and higher throughput, fundamentally boosting GPU utilization and performance. Each optimization in Prism contributes measurably. Engine reuse cuts activation time for a 70B model from 7.2 to 1.5 seconds. Global scheduling balances the GPU load, preventing overloading and idling. Local scheduling, with its priority-based admission, improves SLO attainment for critical models by over 40%. These individual contributions are essential for Prism's overall effectiveness. Prism's design is compatible with next-generation hardware and heterogeneous clusters. Future hardware like NVIDIA GH200 will further reduce activation latency. We currently use NVIDIA MPS for compute sharing and plan to incorporate dynamic SM limit adjustments. Prism also supports heterogeneous GPU clusters, and we are exploring SSD-based weight storage with pipelined loading for even larger deployments. In conclusion, Prism delivers over 2x cost savings and a 3.3x SLO attainment improvement through flexible cross-model memory coordination and two-level demand-aware scheduling. Prism achieves 99% TTFT and TPOT with only 16 GPUs, requiring significantly less hardware than baselines. Built on SG Lang, a prototype will be released to the community to empower cost-efficient LLM serving.